There's a train in Japan that holds the world speed record for rail travel, 603 kilometers per hour. It floats 10 centimeters above its guideway, touching nothing, held up by fields coming off coils chilled to within a few degrees of absolute zero. And every journey it makes, it starts on rubber tires, not as a backup. As standard procedure, the fastest train we've ever built rolls out of the station on wheels, like a bus. Only once it's built up to about 93 miles per hour do those wheels fold away and the train finally lifts. People look at that and assume it's a compromise, a cost-saving shortcut that some better system will eventually design away. It's none of those things. Those wheels are there because of a problem in physics. So, backward that when engineers first ran the numbers in the 1960s and 70s, some of them walked away thinking magnetic levitation might never work at all. Not because levitation was hard. Levitation turned out to be the easy part. The problem was that the same mechanism producing the lift also produced an invisible force holding the train back. A force that got stronger the faster you went, until at a certain speed, it didn't. This is the story of magnetic drag, a curve that runs backward from everything you know about moving through the world, and the reason the fastest train on Earth starts every trip on rubber. Start with what you already understand about resistance. Push a boat through water. The faster you push, the harder the water shoves back. Ride a bike into a headwind, double your speed, and the air resistance roughly quadruples. Aerodynamic forces climb with the square of velocity, go faster, and the universe pushes back harder, always. So when engineers started designing magnetically levitated trains, they were chasing one thing above all else: getting rid of the other drag, rolling resistance, the friction of steel wheel against steel rail, the squash of the contact patch, the grinding of one surface against another. Lift the wheels off the ground, the thinking went, and you delete a whole category of loss. You'd still fight the air, but nothing else. That was the promise. Frictionless transport. What they found instead was that lifting a train with magnets doesn't buy you a free ride. It creates a brand new force pushing back, one that has nothing to do with air and nothing to do with any surface touching any other surface. It's made of pure electromagnetism, and it shows up the instant the train starts moving. To see where it comes from, you need the mechanism. The idea was born, fittingly enough, in a traffic jam. It came to Dr. James Powell in 1960, sitting stuck on the Throgs Neck Bridge on his way to Boston. Powell was a physicist at Brookhaven National Laboratory. He took it to a colleague, Gordon Danby, who had built magnets for what was then the most powerful particle accelerator on Earth. In 1966, the two of them published the first paper on superconducting maglev. They filed for a patent in 1968, and it issued the following year. Japanese national railways started building on that work around 1970. Their insight was clean. Don't put powerful electromagnets in the track, put them on the train. And make the track out of something simple and passive. Loops of aluminum, coils of wire, nothing energized, nothing controlled. Then let motion do the work. Here's how that works. There's a law worked out by Michael Faraday in the 1830s. A changing magnetic field creates an electric current in a nearby conductor. The important word is changing. A magnet sitting still next to a copper loop does nothing. A magnet sweeping past that same loop drives current through it. Now add the second half, sometimes called Lenz's law. The current that gets created always flows in whatever direction opposes the change that made it. The conductor resents being disturbed. It builds its own magnetic field, aimed squarely at fighting the field that showed up. Put those together, and you have levitation. A train carrying enormously powerful superconducting magnets moves along a guideway lined with passive coils. Each magnet sweeping past each coil drives a current. That current makes a field. That field pushes back against the train. Push hard enough and the train rises. The beautiful part is that it's passively stable. If the train sags toward the track, the fields interact harder and shove it up. If it climbs too high, the interaction weakens and it settles. No sensors, no control loop. The physics fixes itself, and the gap it holds is generous. The train floats a full 100 millimeters, about 4 inches, clear of the guideway. But look hard at what just happened, because the problem is hiding inside the elegance. Those currents are real currents, running through real metal. Real metal has resistance. Current pushed through resistance makes heat, and heat is energy that has to come from somewhere. It comes from the train. Every coil the train passes steals a bite of its kinetic energy to power the current it just created. Thousands of coils per kilometer, and you get a continuous, invisible force holding the vehicle back. And you can't separate it from the lift because they're both consequences of the same current. The lift is the point. The drag is the receipt. So here's the obvious question. If drag climbs with speed, and every other kind of drag does, then a train generating its own drag by moving should get brutally harder to push as it accelerates. At 500 kilometers per hour, the magnetic resistance ought to be crushing. This is where the paradox lives. Magnetic drag does climb as the train speeds up. It climbs steeply. It hits a maximum at a specific velocity engineers call the drag peak, and then it falls. Past a certain speed, going faster makes the magnetic resistance smaller. The wall doesn't thicken as you accelerate into it. It thins out. It comes down to timing. When the train is crawling, each magnet lingers over each coil. The field changes slowly, a modest current gets created, and that current has all the time in the world to circulate, hit the coil's resistance, dump its energy as heat, and die. The system behaves like a resistor. Energy pours in and gets burned. Lots of loss, almost no lift. Speed up, and the encounter turns violent and brief. The field slams through in a fraction of the time. Faraday's law rewards that with a much bigger current, which means much more lift. But now the coil's inductance, its built-in stubbornness about changing current quickly, starts to dominate over plain resistance. The current gets created, throws out its field, and gets swept away before it's had time to bleed much energy into heat. The system stops acting like a resistor and starts acting like a spring. It takes energy in and hands most of it back. That's the inversion. At low speed, the track eats the train's energy. At high speed, the track borrows it and returns it. The lift keeps climbing, the loss keeps shrinking. And with a well-built guideway, null-flux coils have been shown to deliver lift-to-drag ratios as high as 200 to 1, 200 newtons of levitation for 1 newton of drag. So at cruising speed, the paradox resolves in the train's favor. The disaster is on the way up. Below the drag peak, an electrodynamic maglev is in the worst state it will ever be in. Maximum magnetic drag, almost no useful lift. Held back hard and lifted barely at all. And the numbers weren't small. For an urban vehicle weighing 20,000 kilograms, a lift-to-drag ratio of 30 at 50 kilometers per hour works out to a drag force of around 6,500 newtons, and a drag power north of 90 kilowatts. 90 kilowatts spent fighting the guideway at a speed a city bus manages without breaking a sweat. In one full-scale superconducting system, the electromagnetic drag peaked at roughly 9 kilonewtons. And at the very bottom of the range, it isn't just wasteful, it's dead. At slow speeds, the voltage induced in the guideway is too low to drive enough current, so no useful force gets produced at all. At a standstill, the current is zero, and a train with no relative motion levitates about as well as a brick. So the brief handed to engineers in the 70s read something like this. Build a vehicle that can't hold up its own weight until it's already moving at highway speed, and which meets its maximum resistance during exactly the phase where it has to get from zero up to that speed. Every launch is a fight through the worst part of the curve, and you have to win it before the technology gives you anything at all. That's how magnetic drag nearly sank the concept, not by making high-speed travel impossible. At speed, the physics is spectacular. It nearly sank it by turning the first 90 seconds into a problem no amount of elegance could dissolve. A frictionless train that can't get moving isn't a train, it's a demonstration. There were two ways out. Japan's engineers took both. The first one looks like surrender. If the system can't hold the vehicle up below a certain speed, then below that speed, don't ask it to. Put wheels on the train. Stopped. The train sits on rubber wheels. To get going, it rolls forward on them, letting the onboard magnets start working against the guideway coils. Once it hits roughly 150 kilometers per hour, the magnetic force is finally strong enough to lift it. Above that, physical contact with the track disappears completely. Easy to read that as a compromise, but look at what it pulls off. Rubber tires are superb at exactly what magnetic levitation is worst at, which is making usable force at low speed. And magnetic levitation is superb at what tires can't survive, which is 500 kilometers per hour, where a spinning wheel becomes a structural liability. The train isn't one vehicle with a weakness. It's two vehicles sharing a body, each handing off to the other right where its advantage runs out. The wheels aren't a failure of the dream, they're the price of admission to it. The second escape actually solved the physics. Wheels get the train through the valley. They don't make the valley shallower. For that, engineers went after the drag itself. And the tool they picked up wasn't more power, it was geometry. The levitation system uses coils wound into a figure 8 along both walls of the guideway, cross-connected underneath the track. They're called null-flux coils, and the trick is what happens at the crossover point. When the train's magnet sits perfectly centered, the flux through the top half and the flux through the bottom half cancel out exactly. Net current, 0. No current means nothing dissipated, and nothing dissipated means no drag. At the equilibrium position, the coil is electromagnetically invisible. Knock the magnet off center, say the train sags a few millimeters, and the cancellation breaks. Current floods the coil and throws out a restoring force that shoves the vehicle back to the middle. This is the crucial move. A conventional coil is making current and therefore drag all the time. A null-flux coil only makes current in response to error. Hold the line and it asks for almost nothing. Size those coils correctly, and a large share of the drag can be eliminated, which is how the 200-to-1 figure becomes reachable. And the same geometry needs only one set of guideway coils to do 3 jobs at once: levitation, side-to-side guidance, and working with the propulsion system. The engineers didn't beat magnetic drag by overpowering it. They beat it by building a system where, most of the time, there's nothing for the drag to grab hold of. Getting from that insight to a working railway took decades. A test track went up at Miyazaki in 1977, and in 1979, the first vehicle set a world record of 517 kilometers per hour running unmanned. One test vehicle was lost completely to a fire in October of 1991. Magnet quench turned up at Miyazaki, traced to vibration during running, and was engineered out before the Yamanashi line. But the curve got conquered. On the 21st of April 2015, a crude 7-car L0 series train reached 603 kilometers per hour, breaking the previous record of 581 from 2003. That record isn't raw power, it's the right side of the drag curve. The region where lift is enormous, magnetic resistance has collapsed to almost nothing, and the only opponent left is the air. And the commercial line is a reminder that physics was never the hardest part. The Chuo Shinkansen is designed to run at 505 kilometers per hour, from Tokyo to Nagoya. Opening is now expected in the mid-2030s at the earliest, against an original target of 2027. No new date has been announced because excavation hasn't started in the Shizuoka stretch of the Southern Alps tunnel. The delay isn't electromagnetic. It's a tunnel, a watershed, and a prefectural government. So come back to where we started, a 600-kilometer-per-hour train rolling out of a station on rubber tires. It isn't an embarrassment. It's a signature. The visible mark left on a machine by an invisible force that runs backward from everything your instincts expect. A resistance that grows as you accelerate, peaks, and then dissolves the harder you push. A wall that thins the faster you run at it. Powell and Danby described a train that would ride on nothing. What they'd actually invented was a vehicle that has to earn that condition, one that fights through its own worst physics before the physics turns around and starts working for it. Every journey, the same bargain. Wheels for the first 93 miles per hour, then the ground lets go.